Welcome to the 6th lecture on homology theory. So today I shall start with one interesting result. So let's write the statement. So it says if X is a non-empty and path connected topological space, then the zeroth homology of X is isomorphic to Z, that is the group of integer. So here is the proof. So first of all, what is the definition of H0x, that is zeroth singular homology of X? So by definition, H0 of X is kernel of del 0 quotient with image of del 1. But we know that del 0 is just a 0 map, right? So therefore this is just C0x quotient with image of del 1. So you can write as C0x to 0 del 0 is a 0 map. Okay. Now we define one homomorphism. So define a homomorphism. Say the group is epsilon, the map epsilon from the group C0x to Z by, we define by say epsilon of summation I, say I equal to 1 to say m. This is a finite sum, we know. So ni sigma I. So what is my sigma I? Sigma I is singular 0 simplices. Okay. So this is equal to summation of ni. Okay. Now it is easy to verify that this is a homomorphism. Now first we prove that this homomorphism is also a surjective one. This is also trivial to see, but we shall prove this one. So the proof is very trivial, and we will use that X is non-empty. So since X is non-empty, so therefore we have an element X in the set X in a topological space X. Okay. Now let sigma be a constant map sigma from del 0. So what is del 0? It's delta 0. So delta 0 is just 0 simplex. Okay, it's just a 0 simplex, it's just a vertex to the singleton set X. Okay, which is subset of X. So this sigma is a constant map from delta 0 to X, right? That means sigma of delta 0 or sigma of that vertex equal to X. So this is a constant map. So we can say that this sigma is a singular 0 simplex. Okay. So that implies, so this implies sigma belongs to C0x. So C0x is non-empty. Okay. So if X is non-empty, then C0x is also non-empty. Now for each n belongs to z, that is for each integer n, we have that n sigma belongs to C0x, right, because sigma is in C0x and C0x is a free group generated by many elements and one of them is sigma. Okay, so n sigma belongs to C0x, and by our definition that epsilon of n sigma will be n, right. Therefore, for each n in Z we have a preimage. So that implies this sigma is surjective. Therefore, we can say that sigma from C0x to Z is a surjective homomorphism. Okay. Now we use one fundamental result. So if we have a surjective homomorphism, then we can deduce one isomorphism, right. Now that implies that sigma bar from C0x quotient with kernel of epsilon to Z is a isomorphism. In other words, we can say C0x quotient with kernel of epsilon is isomorphic to Z. Okay. Now, if we can show that kernel of epsilon is same as image of del 1, then we have that H0 of x, which is by the definition C0 of x quotient with image of del 1, right. And if we prove that kernel of epsilon equal to image of del 1, then that will be C0 of x quotient with kernel of epsilon, and we have already proved that this is isomorphic to Z. That's mean to prove that H0 of x equal to Z, that is isomorphic to Z, it is sufficient to prove that kernel of epsilon is equal to image of del 1. So now we claim that kernel of epsilon is same as image of del 1. Okay. So first we prove this one, this portion, that is image of del 1 is subset of kernel of epsilon. Okay. So we prove this first. So let sigma belongs to image of del 1. Okay. Now since sigma belongs to image of del 1, that imply sigma equal to del 1 tau, right, where tau belongs to C1x, right. So that's mean say tau equal to say summation I equal to 1 to some number m n I tau I. Okay. So where tau I are the singular one simplices, that's mean tau I are mapped from delta 1 to x are singular one simplices. Okay. So that's mean sigma equal to del 1 of tau, that is summation I equal to 1 to m n I del 1 of tau I. Okay, so this del 1 we can write this is as say v0 v1. Okay, so to define the map we need some vertices, so let the vertices are v0 v1, then that will be summation I equal to 1 to m n I tau I restricted over that v1 minus tau I restricted over v0. Okay, so in short you can write it is as summation n I tau I restricted over v1, that is these are singular zero simplices, right, minus again summation I equal to 1 to m n I tau I restricted over v0, that is it is also singular zero simplices. Now that will imply epsilon of sigma, that is, so sigma is this minus this, right, so we have to take the coefficient only, so that will be summation of ni minus summation of ni, so that is 0, right. So we assume that sigma is in image of delta 1 and we find then epsilon of sigma equal to 0, that's mean sigma belongs to kernel of epsilon, so that is image of del 1 is subset of kernel of epsilon. So now we prove the other way, that is kernel of epsilon subset of image of del 1. Okay, so again, so let sigma belongs to kernel of epsilon. Okay, so what is kernel of epsilon? So this is a subgroup of C0x. Fine, that's mean sigma is equal to summation over I equal to 1 to some m, okay, some number m, such that this is summation of ni sigma I, where sigma I is zero simplices, right. So each of sigma I, say from v0 to x be a 0, or you can write singular zero simplex, zero simplex. So let sigma I v0 equal to xi, that is a point belongs to x, right. So that's mean since sigma I, the domain of sigma I is a vertex, so the image is also a vertex, and that sigma I is uniquely determined by the image, that is because image is a point, right. That's mean if we have any singular zero simplex whose image is xi, then that singular zero simplex should be my sigma I. Fine. Okay, now it is given that sigma belongs to kernel of epsilon, so that imply epsilon of sigma, that is summation of I equal to 1 to m ni sigma I, that is 0, that imply summation of I equal to 1 to m ni, this sum is equal to 0. Okay, right. Now we have the elements x1 x2 up to xm in x. Now we choose another x, say arbitrary x in x. Okay, so this a point. Now let us define a map, say sigma 0 from delta 0, which is just say vertex v0, to x be a map such that sigma 0 of that v0 is equal to x. That's mean the map sigma 0 is uniquely determined by the point x. That's mean if we have any singular 0 simplex whose image is x, then that singular 0 simplex should be sigma 0. Fine. Okay. Now we use that x is path connected. The topological space x is path connected. Since x is path connected, so there exists a continuous function, say tau I, from any any closed interval to x. So we can write that closed interval as v0, v1. Okay, that is a line segment from v0 to v1 to x such that tau I v1 equal to xi and tau I v0 equal to x. Okay, so that's means since x is path connected, so tau I is just a path from x to xi in x. So we can write that is tau I is a path from x to xi in x. So since x is path connected, so we can find such a path, right? Now since the domain of this path is just a closed interval, so we can write that domain as an edge, right, as an delta 1. Okay. Now here, so if we take this tau I and if we take restricted over that v1, okay, now what will be this map? Now this map will be a map from a vertex to the point xi, right? But we know that any singular 0 simplices whose image is xi is actually sigma I, right? So this is my sigma I, and if we take tau I restricted over v0, then this is sigma, right? Why? Because both are singular 1 simplices and whose images are same, right? And that image is just a vertex, right? So both are singular 0 simplices and the constant map, so they are same. Now we define a map, so let tau equal to summation I equal to 1 to m ni tau I. Now obviously each tau I is a singular 1 simplices, right? Now since each tau I belongs to, or you can say is a singular 1 simplex, right? That imply tau belongs to C1x. Okay. Now what will be my del 1 tau? That is what will be the boundary of this tau. Now del 1 of tau will be del 1 of that summation over I equal to 1 to m ni tau I. Okay, and that will be summation I equal to 1 to m ni del 1 tau I, that is summation I equal to 1 to m ni, and then tau I restricted over v1 minus tau I restricted over V0. Okay. Now that is, we have already seen that. So summation I equal to 1 to m n I, and tau I restricted over V1, right? Its image is xi. So this is sigma I. We have already seen this, right? So that is sigma I, and this is my sigma 0. So we have defined sigma 0, I think, right? Right. So sigma 0. So there was a misprint here. So this should be sigma 0. Okay. So that's mean this will be equal to summation over I equal to 1 to m n I sigma I minus summation over I equal to 1 to m n I sigma 0. Now that part, this part is sigma, right? You can check where is my sigma. So this is my sigma, right? So this part is sigma and this part is 0, because if you take sigma 0, it is a constant one, right? So it is sigma 0 and summation over I equal to 1 to m n I, and this is just a 0. So this is sigma. Okay. So that imply we have del 1 of tau equal to sigma, and tau belongs to C1x. So that imply sigma belongs to image of del 1. So we assume that sigma is in kernel of epsilon, and we prove that sigma is in image of del 1. So that is kernel of epsilon subset of image of del 1. So therefore we have kernel of epsilon equal to image of del 1. And now we are done. So therefore A0 of x, which is by definition C0 of x, quotient with image of del 1, and we have proved that image of del 1 is same as kernel of epsilon, and we have already proved that this part is isomorphic to z, right? So that is A0 of x is isomorphic to z if x is non-empty as a set and path connected. Okay. So from this we have a corollary. So if x alpha, say alpha belongs to some index set lambda, be the path component of a topological space X, then A0 of X, which is direct sum of alpha A0 of X alpha, right? So we have proved this in the last lecture, and since each of X alpha is path connected, so A0 of X alpha is Z, so we will have Z, right? That's mean the number of the copies of Z is same as the number of the path connected components of a topological space. Fine. Now we prove one interesting result. It says, so let X and Y be two topological space then a map, that's mean a continuous function f from the topological space X to Y induces a homomorphism say f star between the group, or we can say from the group Hn X to Hn Y, and this is true for all n. Okay. Now more specifically we can write here f n star, because if n varies then f star will change, right? But to avoid the notation we can just write f star. Okay. But you have to remember that the f star from say f0x to h0x to h0y is different from f star h1x to h1y. Okay. So to avoid the notations I am writing here only f star. So first of all, see that if we have a singular n simplex is x, so let sigma delta n to x, that is a map from delta n, that is a n simplex to x. Okay. So let this sigma be a singular n simplex in x. Now throughout this talk I use sigma for singular n simplex as well as singular n chain. Okay, but I will define when I am writing it is when I consider sigma as a singular n simplex and singular n chain, but don't be confused about that. Okay, so this time I am considering sigma as a singular n simplex. That means sigma is a continuous function from delta n to x. So we have delta n to x then y. So this is my sigma, right? And this is the function f. So that sigma and f both are a continuous function. Now that imply if you compose these two continuous function, then you will have f sigma. This is a function from delta n to y. Okay. So the composition of two continuous function is continuous. So this is a continuous function. That's mean this is a singular n simplex in y. Right? So if sigma is a singular n simplex in x, then f sigma is a singular n simplex in y. Now we use this fact to define a homomorphism from Cnx to Cny. Now we define a homomorphism if we write f hatch from Cnx to Cny by the following way. Note that here also if n changes then f hatch will change, right? So it is better to write f n hatch. Okay, but anyway throughout this lecture, even throughout the book, if you check that generally they omit that n to avoid the notations. Okay, so I am also just avoiding that notation n. So there is no harm to avoid such notations. Now we have to define a homomorphism, right? So we have to choose one element from Cnx, but we know that the element of Cnx is a singular n chain. Okay, now let sigma belongs to Cnx. Now note that that sigma may not be a singular n simplex. So it is a singular n chain. So there is a difference between singular n chain and singular n simplex, right? So that is sigma can be written as a finite sum. I am just writing summation I. Okay, but this sum is finite. Ni sigma I, where ni are the integers and sigma I, each of sigma I is a singular n simplex in X. Okay. Now we define f of h of sigma equal to that summation I ni f of sigma I. Okay, but we have already seen this here, right? So if sigma is a singular n simplex in X, then f sigma is a singular n simplex in Y. Therefore this is a that f of sigma I is a singular n simplex in Y, right? So that imply, so this is a that sum is a singular n chain in Y and hence belongs to Cn of Y. Okay, so this way we can define a homomorphism from Cnx to Cny. Obviously here I define only a map, but you have to check that it is a homomorphism. But though it is a very simple, it is very trivial to check that this is a homomorphism, but still I can do it for you. This is a simple one. It is better to avoid. Okay, so first of all, let sigma tau belongs to Cnx. Okay, that's mean sigma equal to summation, that finite summation of ni sigma I, and tau is finite summation of say mi, say mj, say tau j. Okay, where sigma I and tau j are singular n simplex in X. Now what is my f of h sigma plus tau? Now that will be f of h, the all of this summation, so ni sigma I plus summation mj tau j. Now again this is a singular n chain in X, right? And both sum are finite sum, so their summation is also a finite sum. Therefore by definition it is summation I ni f of sigma I plus summation mj f of tau j, right? And this is f of h sigma plus f of h tau. So this is a homomorphism. Fine. We can write that. So thus fh is a homomorphism. See, the proof is very simple, right? It is trivially follows from the construction, or you can say definition. Now for a singular n simplex sigma in X, we can define a boundary, right? Boundary of that simplex. So we can write this sigma from delta n to x, right? Since we need to define the boundary, so better to write delta n in terms of vertices. So sigma is a map from v0 to vn, this simplex, this n simplex to x. Okay. So for a singular n simplex sigma, now del n sigma, since here we have x and y both, so for a time being we can use one extra notation, okay, for the clarity. Say this is x, okay, but you can omit that x as well, even you can omit this n as well, it is up to you. But here I am writing that x and y to be more specific, okay. Now this will be, by the definition, summation I equal to 0 to n sigma, right, restricted over v0 vi cap, that's mean vi vertex is missing, and vn, this one, right. Now since this is a sum, so this sum is not a singular n minus 1 simplex, right. So this is a singular n minus 1 chain, right. Now we can use the induced homomorphism f hatch from Cnx to Cn minus 1x to Cn minus 1 y, okay. So f of h del n x sigma equal to f of h summation I equal to 0 to n sigma restricted over this. Okay. Now note that if you want to be more specific, you can use here n minus 1, right? Because the f hatch which we applied before, it is different from this, because f hatch we defined earlier from Cn to Cn, but it is from Cn minus 1 x to Cn minus 1 y, right? So therefore you can write here f hatch n minus 1 and previously f hatch n, but it is fine if you omit this portion to avoid the notation. Okay. Now by definition this will be summation I equal to 0 to n f of sigma restricted over v0 vi cap vn. Now note that sigma restricted over this was a singular n minus 1 simplex, and we apply f here, therefore f of sigma and restricted over this will be a singular n minus 1 simplex in y, right? Therefore this is a singular n minus 1 simplex in y, and we are taking that summation. So that's mean by the definition you can write this is as del n, obviously this is the del function in y, this is the boundary map in y, and f of sigma. Fine, is it clear, right? See, this is one n simplex, right? So sigma is a n singular n simplex in x, so f of sigma is a singular n simplex in y. Now if you apply this boundary map you will get this, okay, fine. So that's mean f hatch del n x, this one sigma equal to del n y f of sigma, this one. Now again sigma is a singular n simplex in x, and you can consider this is as a singular n chain as well, right? That's mean you can write it is as f hatch sigma. So therefore f of hatch del n x sigma equal to del n y f of hatch sigma. Fine, where sigma is any singular n simplex in x. Okay. Now since Cnx is generated by this sigma, so we can write that this function is same as this function. Okay. But anyway, if you don't get it, then also I can prove it. But again it is a very trivial, so better to skip. Okay. So okay, I am proving this one. So why this map will be same as this map. So first of all, let sigma be an arbitrary element in Cnx. Now since sigma is an arbitrary element in Cnx, then sigma can be written as finite sum of ni sigma I, right, where each sigma I is a singular n simplex in x, and this is a singular n chain in x. Okay. Now if you apply f of hatch del n x of sigma, that's mean it will be f of hatch del n x summation of ni sigma I. Okay. Now you can apply first del n and then f hatch, but we know that del n is a homomorphism, right? So by the definition we define del n as a homomorphism. So therefore it will be f hatch summation ni del n x sigma I. Okay. Now again we know that f hatch is a homomorphism. Therefore again it will be summation ni f hatch del n x sigma I. Okay. Now this is a singular n simplex, and for singular n simplex we have already proved that it's commute, right? Now we will use that fact. Now that will be summation ni del n y f of hatch sigma I. Okay. So this commutes and it's come from this. Okay. Now that will be again if we take delta n out of this summation, since delta n y is homomorphism, so it will be delta n y summation ni f hatch sigma I, and again it will be del n y f hatch, since it is a homomorphism, summation ni sigma I and that is del n y f h sigma. Since this equality is true for all sigma belongs to Cnx, therefore we can write f h del nx is same as del ny f of h. Okay, fine. So we are done here. Now if we want to be more precise, then we can write this equation as, so f h that n minus 1 del nx is equal to del n of y f h that is n for all n. Okay, so more specifically this is this equation, but here I have omitted the symbol n. Okay, so it is well understood. Anyway, you can write this one, and also you can avoid all of this n and x. So also one can omit this, all of this n and x and y. So one can write it as f h del equal to del f h, and in this sense we can say that f h and del commutes with each other. Okay, so these are the notations only. So if it is well understood, you can exclude that n or x. Okay, but here I need del n x and del n y. That is the reason I am writing this. So you will see this now. So why I am writing del n x instead of only this del. Now first of all, we have a homomorphism f h from Cnx to Cny, right, and which commutes with delta. Fine. Now I shall show that this f h sends that kernel of del n x to the kernel of del n y. Okay, that's mean we prove, or you can say we show, that this f h sends that kernel of del n x, which is subset of Cnx, to kernel of del n y, which is subset of Cny. Okay, why it is? This is also simple. So first of all, let sigma belongs to kernel of del n x. Okay, so that's mean del n x sigma equal to 0, right? Now what about del n y f h sigma? Now what about this one? Now this is same as del n y f h sigma, right? And we have already seen that this is commutative, so that is f h del n x sigma, right? We have seen that, this one. Now that is f of h del n x sigma, but we have seen that here del n x sigma equal to 0. So that is, it is 0. So f h of 0, so this is 0. So that imply f h sigma belongs to kernel of del n y. So if we choose an element from kernel of del n x, then f h sends that element to kernel of del n y. Therefore, if we take the restriction map, so we can write thus we have a homomorphism f h, say it is different one dash from kernel of del n x to kernel of del n y. So this is just the restriction map of f of h. So we can write here, which is just a restriction of f of h over kernel of del n x, which is subset of C n x. Fine. Now note that here I shall use one fundamental result of algebra, not fundamental theorem of algebra, one result. So first of all, if G is a group and N is a normal subgroup of G, then there is a homomorphism say H from G to G quotient N defined by G going to Gn. Now you can easily check that by using that N is normal, it is a homomorphism. This is a trivial, okay, this is a trivial result in algebra. Now I shall use that one. So what I shall do, so kernel of del n x to kernel of del n y, we have a homomorphism, say it is f h dash, right? Now from this to we have some homomorphism this to kernel of del n y quotient with image of del n plus 1 y, right? We know this is a normal subgroup of kernel of del n y, right? So there is a homomorphism. So both are homomorphism. So here f h dash and h both are homomorphism. Right? So that is we have a homomorphism we can write f say h say double dash from kernel of del n x to kernel of del n y quotient with image of del n plus 1 y, such that sigma goes to f h sigma plus image of del y n plus 1. Okay. Now what is the zero element of the codomain? The zero element of the codomain is that quotient group, right? That is just image of del n plus 1. Now I shall use another result of algebra. So if say H G to H be a homomorphism and let that N is a subgroup of kernel of H, then there is a homomorphism say H bar from G quotient N to H. Okay, so I shall use this result and I prove that image of del n plus 1 x is a subgroup of kernel of this map. Okay. So first of all, let sigma belongs to image of del n plus 1 x, and obviously this is subset of kernel of del n x, right? That means it is in the domain. Now we prove that this is subgroup of kernel of f hat double dash. First of all, since sigma belongs to image of del n plus 1 x, therefore so there exists tau belongs to C n plus 1 x such that sigma equal to del n plus 1 x tau, right? Therefore, what is my f of hatch of sigma? So f of hatch of sigma will be f of hatch of del n plus 1 x tau, right? Now this is commutative, so it will be del n plus 1 y f of hatch tau, right? Now this one is a element of Cn y, Cn plus 1 y, right? And we are applying the boundary, so therefore it will be belongs to image of del n plus 1 y. Therefore, what will be my f hatch double dash sigma? So that will be, see here, it is f hatch sigma plus image of this. So it will be f hatch sigma plus image of del n plus 1 y, right? Now since this is an element of this, therefore this is just image of del n plus 1 y, that is the zeroth element. So that imply sigma belongs to kernel of f hatch double dash. So we can write image of del n plus 1 x, that is a subset of kernel of f hatch double dash. Now since both are groups, so image of del n plus 1 x is a subgroup of the kernel of f hatch double dash. Okay. Now we can use this result in this map. Okay. So we will have, we can write, So therefore there is a homomorphism f star from kernel of del n x quotient with image of del n plus 1 x to kernel of del n y quotient with image of del n plus 1 y, and this is hn x and this is hn y, right? So we are done. So that is f star hn x and to hn y, right? Therefore f induces this homomorphism. Thus f induces the homomorphism f star hn x to hn y. Okay. Now by the construction it is easy to verify that. You can just check that. So first of all, if that x to y we have a map say G, and y to z we have a map say F, then so they are maps, then that F compose G, this star equal to F star composition G star. You can easily verify this, and you have to use here that delta n to x to y to z. So this is my sigma, this is my G, this is my F. Okay, so since you can easily check that by the construction, okay, so all of these maps are just additive, right, in terms of homomorphism. Therefore you can easily verify this one. And another one is, so for the identity map I say x to x we have I star which is from hnx to hnx is also identity, and this is also very easy to verify, because if you have identity map then nothing will be changed, so you will get the identity function from or identity homomorphism from hnx to hnx. Okay, so these two are very trivial and it follows from the construction, and here we can just use that associative property. Okay, so this is very simple, so you can just go through the proof and you can easily verify this one. So I stop here, see you in the next lecture.